Hi guys, so today we're doing lesson 4.3. We are going to learn a new method of dividing polynomials called synthetic division. We are also going to learn about a couple theorems, so remainder theorem, factor theorem, and rational roots theorem. So pretty big lesson. Here is today's warm-up. You're going to review long division of polynomials by dividing this x cubed plus 4x squared plus x minus 6, all of that divided by the polynomial x plus 2. So go ahead and take a couple minutes to do that, and then you can rewatch this video or play it again to make sure you're doing it correctly. Okay, so the first thing I always want to make sure of is that both the dividend and the divisor are in descending order of exponents and that I'm not missing any exponents. So I have x cubed, x squared, x to the power of 1, and then my constant. I have x to the power of 1 and then my constant here. So I'm not missing any of those terms, which is great. I'm going to just go ahead and set this up then, so that I have it written in the correct format. Okay, and remember, we start by looking at this very first term, x, and dividing that into the first term underneath this division symbol. So x times what gives us x cubed? Well, that would be x squared. Then we take that x squared and we multiply that times this entire thing. So x squared times x, we just said, is x cubed. And we also have to multiply x squared times 2 gives us a positive 2x squared. Remember, at this point, when we subtract, we need to flip the signs. So subtracting is the same thing as changing the sign. So this becomes a negative, and this also becomes a negative. So x cubed minus x cubed is 0. 4x squared minus 2x squared is a 2x squared. And then I carry down what I'm left with. So the plus 6, or the plus x minus 6. Okay, now I go back to here, I look to see x times what gives us the 2x squared. Well, just a positive 2x. And again, I take that 2x, and now I multiply that times this whole thing, so times x plus 2. So 2x times x is 2x squared. 2x times 2 is positive 4x. And then again, we need to subtract this. So this changes signs, this changes signs. Again, as you saw in the last video for long division, you can, like I'm doing here, circle what the final sign is. I just like to do that. That way I'm not guessing. Okay, so that gives me 0. X minus 4x is negative 3x. Carry down the minus 6. And then one more time, I look to see, okay, x times what gives me the negative 3x? Well, a negative 3. Take this negative 3 and make sure you're including that negative sign when you multiply that times this entire thing over here. Let me just erase this so it looks a little bit less messy. Okay, so negative 3 times x is negative 3x. Negative 3 times 2 is negative 6. Again, I flip the signs one more time, so negative times negative becomes a positive. Same thing here, a positive. And then negative 3x plus 3x is 0. Negative 6 plus 6 is 0. So I have a remainder of 0. If I did have a remainder, I would need to add it up above here, subtract it depending on that sign, and then have that all divided by this divisor. But because it's a remainder of 0, I can just write this answer, x squared plus 2x minus 3. Okay. So let's go ahead and move into a new method of division, synthetic division. The reason that we teach you this in addition to long division is because it's a lot faster, and students tend to like it just because it's a little bit simpler. However, we still have to know long division because synthetic division only works for specific cases of polynomial division. So when we're dividing a polynomial by a binomial, that's just a fancy way of saying a polynomial with two terms. So think by, like bicycle has two wheels. So if it is a binomial, dividing by a binomial that's in this form of x minus some number c, then we can streamline the division process and use synthetic division. So synthetic division only works when we are dividing by a binomial that looks like this, x minus c. Really just meaning x plus or minus a number, okay? Or x minus a number. So that can be a plus sign there. Does not matter. All right, so here are the synthetic division steps. You by no means need to write all of these out. I just wanted to show you this. So you do have this on a slide. If you need to come back to this or reference this to see all of the words written out, that's great. I do have an example right here that I'm going to just kind of talk through briefly, and then we'll actually practice a couple examples. So just like with long division of polynomials, the first thing is to make sure you arrange the polynomial in descending order of the powers or exponents. And if there are any missing terms, you need to add in those terms with a coefficient of 0. Okay, then we're going to take whatever c is. So if we have a divisor of x minus c, we're going to take that c term, and we are going to write it over to the left side, just like you see here. So we're dividing by x minus 5. So c is the opposite sign. So it's minus 5, x minus 5. So c is a positive 5. So we take that c term and we write it over here to the left side, and we kind of box it off with half a little box right here. Okay, then we are going to write the leading coefficient of the dividend. So what we're starting with, we're going to write the leading coefficient, and we're going to put that in this top row. So all of those coefficients here. So this is a 1x cubed, a negative 2x squared, a negative 8x, and a negative 35. So we take those coefficients, we write them in this top row right here. And we remove the x cubed, x squared, x's, all the variables. All right, then we begin the process of synthetic division. Okay, so this is where you'll just learn this method, and at first it seems a little bit weird, but I promise as you practice, you'll pick it up really quickly and probably enjoy it more so than long division. So then we multiply c, right here, our 5, times the value underneath the row. Okay, first thing I forgot to say, we carry down this first leading coefficient. So we write that down, we carry down the 1, and then we start multiplying the 5 times this bottom row. So 5 times 1 is 5, and we put that up here. And then, just like this is a big addition problem, we add these down. So negative 2 plus 5 gives us 3. Then we go back to this process, and we multiply 5 times 3. And that gives us 15 here, okay, and then we add down. So negative 8 plus 15 gives us 7. Then we go back here, we take the 5 and we multiply 5 times 7, which is 35, and then we add down, and negative 35 plus 35 is 0. And whatever is in this last little spot here, I always like to box it off again, that is our remainder. Okay, so we just went through these couple steps. So we multiplied by c, then we added the values down, and we repeated this whole process. The last step is you use all of the numbers in the last row that you get here as the coefficients for your answer. Okay, so the quotient is going to have these as the leading coefficients, and the degree of the first term is 1 less than the degree of what you started with. So this is a third degree polynomial. Okay, if we're dividing by a linear factor like this, just with an x minus 5, then this is going to start out with an x squared term. So this is third degree, so we're going to end up with a second degree polynomial here. So then we write out our coefficients and in descending order. So we have a 1x squared plus then descending order 3 x's, and then plus 7 would be our constant, and we have a remainder of 0. Again, this might not make any sense yet until we actually practice this with our own example, so we will do that just now. Okay, we're going to go ahead and start the process here. First of all, we have to look at both of our polynomials and make sure they're in descending order and we're not missing any terms. So they are in descending order. However, I notice this one has x to the 4th, third, second, but no x to the power of 1 in between this and the constant. So I need to add that in. So first thing I'm going to do is rewrite this with a 0x squared, or sorry, just a 0x added. Okay, and then plus 18. All right, now I take the c term. So it's always the opposite sign, x plus 2, so opposite sign would be negative 2, and I put that in its own little half little box here. okay? Then I'm going to write down the leading coefficients for my polynomial that I'm starting out with. So just the numbers out in front. So 2, this is a 1, x cubed. So anytime you don't have a coefficient that you see there, write it out, please. Negative 16, so carry the sign in front of it, 0, and 18. All right, then I'm going to make a line here. I carry down the 2, and then I'm going to start the process of multiplying. So I multiply my c term, negative 2 times 2, to give me right here. So negative 2 times 2 is negative 4. And then I start adding down. So 1 plus negative 4 is negative 3. Oopsies, let me change colors. And then I repeat the process. So negative 2 times negative 3 is positive 6. Add down, negative 16 plus 6 is negative 10. Negative 2 times negative 10, repeat the process right here. That gives us 20. Add down, 0 plus 20 is 20. Okay, and then negative 2 times 20 is negative 40. That's our last step. Negative 40 plus 18 is negative 22. And then we're going to box this off just like we boxed off our c term, and that there is our remainder. Okay, so we look now at what the degree is going to be of this polynomial. So if we started with x to the 4th power, it's going to be 1 less than that. So this would be an x cubed, an x squared, an x, and then our constant term, and you just go in descending order. So our answer here is 2x cubed minus 3x squared minus 10x. Then we put a sign in between there, plus 20. And again, this is our remainder. So minus 22 all over what our divisor was originally, x plus 2. And that is our answer. So again, synthetic division takes a little bit of getting used to just because the process is a little bit less straightforward than long division, but it's a really cool shortcut or way of dividing polynomials. So let's do one more example. Okay, we'll check to make sure this is in descending order. So we've got a 4, a 3, a 2. We're missing x to the power of 1 again. So we're going to add that in, and then the divisor is good to go. So I'm going to rewrite this as x to the power of 4 minus 9x cubed minus 7x squared plus 0x plus 10. Okay, then I am going to take my c term, so opposite sign, negative 5, put that there. And I'm going to write out my coefficients. So this is a 1, negative 9, negative 7, 0, and 10. So 1, negative 9, negative 7, 0, and 10. Carry down the leading coefficient, and then we start multiplying. So negative 5 times 1 is negative 5. Add that down. We get negative 14. Multiply again. Negative 5 times negative 14, that's going to give us a bigger number of 70. Add down, negative 7 plus 70 is 63. Multiply negative 5 times 63, negative 315. We add down, we get negative 315 because we're just adding that to 0. And then last but not least, negative 5 times negative 315 gives us 575. We add down 10 plus 575. Oh, sorry, not 575, 1575, I apologize, is 1585. Okay, so one of the reasons I put this example in here is just to show you that your remainder is not always going to be a nice, neat, tiny number. It is totally fine to have a pretty large number there or a really small number there. And then, again, we look, this is a degree 4. We're dividing it by a linear factor, so this is going to be a degree 3 polynomial. So 1x cubed minus 14x squared. This is going to be an x term, so plus 63x minus 315, and then plus our remainder of 1585 divided by our original divisor of x plus 5. Okay, so that is synthetic division. We will practice a ton as we use and apply some other theorems that we're going to learn in today's lesson. All right, two theorems we're going to use right now are remainder theorem and factor theorem. So please write these down because they are likely brand new to you. So remainder theorem says if you have a polynomial that is divided by x minus c, then the remainder is also the same thing as f of c, whatever that c term was plugged into the function, okay? So meaning if we go back here, this remainder of 1585, we also could have gotten by plugging c into this if this was a function. So if that was a function, we plugged in -5 to it, we would have gotten this as our answer, as our output, okay? And then factor theorem says if a remainder is 0, so if you divide two polynomials and the remainder is 0, then c, this guy right here, is a 0 or an x-intercept, that's another way of saying that, okay? And x minus c is a factor of the function, okay? And we'll talk about that. That one's pretty straightforward. It's a little confusing when you just talk about it, but when you actually utilize it, it's pretty straightforward. So in essence, when you divide a polynomial by a factor, if it divides into it perfectly and there's a remainder of 0, there's no remainder, then that means it's a factor, and that is also a point where the polynomial crosses the x-axis, or it's a 0. Okay, so let's use the remainder theorem to evaluate a polynomial function. So example number 1, given the function, use the remainder theorem to evaluate f of -4. So obviously we can evaluate f of -4. We could just plug in f of -4 and find out what that is. 3 times -4 cubed plus 4 times -4 squared minus 5 times -4 plus 3. But that also, can be a lot of work depending on the type of polynomial or how long it is. And so instead of doing that, what we can do is use the remainder theorem, which tells us that if we use polynomial division, whatever our remainder is going to be equal to this, okay? So what are we dividing this by? Well, if this is our c term, if c is -4, then x minus c, x minus a -4, would be x plus 4. So remember, c is always the opposite sign of what you see when it's adding or subtracting to x. So if we divide this by x plus 4, then we can use our remainder theorem and evaluate what f of -4 is. All right, so I'm going to use synthetic division here. I'm going to write -4 over here and then all of my coefficients. So 3, 4, -5, and 3. We made sure it's in descending order. We're good to go. We're not missing any terms. So carry down the 3, start multiplying. So -4 times 3 is 12, -12. -12 plus 4 is -8. -4 times -8 is positive 24. Positive 32. -5 plus 32 is 27. -4 times 27 is -108. You can absolutely use your calculator to help you out with this. And then -3 plus -105, or -108 is -105. My mouth is getting ahead of my brain. Okay, so our remainder here is -105. And the remainder theorem says that if we divide by x minus c, then the remainder tells us what f of c is. So it tells us what f of this value, -4, is. So f of -4 is equal to -105. Okay, that is what the remainder theorem helps us to do, which is pretty cool. Again, we could totally find this by plugging in -4 here, here, and here, but sometimes it's just helpful because you might have already within a problem done synthetic division for that c value and found what the remainder is, and so then instead of having to go back and plug that value in again, you might already have that information and have a point that's on the graph. Okay. Using remainder theorem a second time, this says evaluate the function at x equals -1. So this is our new c term. C is -1. All right, so if we are doing this, then we're going to divide by x plus 1, so opposite sign, okay? So we put our -1 here and check to make sure we have all of the terms, and in descending order, we are missing a 0x right here. So I'm going to write that in, plus 0x, okay? So coefficients are -1, 3, 5, 0, and -10. Carry down the -1 and start multiplying. -1 times -1 is 1. Add, we get 4. -1 times 4 is -4. Add 5 plus -4 is 1. -1 times 1 is -1. Add, we get -1. And then last but not least, -1 times -1 is +1. We add that down, -10 plus 1 is -9. Okay, so here's our remainder. And so remainder theorem, again, tells us that the remainder is the same thing as what we get when we plug in the c value for the function. So f of -1 gives us -9. This also tells us that we have the point -1, -9 on the graph. Okay, so when we plug in -1 for x, we get -9 for y. Similarly to here, when we plugged in -4 for x, we got -105 for y. Okay, the other thing I want you to write down from the previous slide is this. Anytime you are writing the solution to, a polynomial being divided, or a function that's a polynomial being divided by a factor, you can rewrite it in this format to where you have whatever your x minus k value is times the quotient plus the remainder. Okay, we'll see some examples of this in a little bit. So r is the remainder, q of x is the quotient, and I'll show you what that means a little bit later. All right, now using both remainder theorem and factor theorem. So this first says determine if x plus 1 is a 0 of the function. Okay, so what we're going to do is we're going to divide it, and we're going to see if it divides into it perfectly, because factor theorem says if the remainder is 0, then it's a factor. So that's what we're looking for here. Okay, so double check to make sure that the polynomial is in descending order and it's got every single exponent accounted for, so x cubed, x squared, x, and then the constant. So we're good. All right, we're going to go ahead and do synthetic division. So let's write these coefficients. Again, I can use synthetic division because I have a factor I'm dividing by that's in the form of x plus c. So carry down the 15, start multiplying. -1 times 15 is -15. 14 plus -15 is -1. -1 times -1 is +1. Plus -3 is -2. -1 times -2 gives me +2. And then -2 plus 2 is 0. Okay, so here's my remainder. So again, using what remainder theorem says, or factor theorem, if our remainder is 0, which it is, that means this factor, x plus 1, it divides into it completely. So x plus 1 is a factor of the function. Okay, so yes, x plus 1 is a factor. That should say factor up here of the function. And x equals -1 is a 0. Okay, so if x plus 1 is a factor, that means x equals -1, the c term, the c value, that is where our 0 is at. In essence, -1, 0 is one of the x-intercepts, or one of the zeros. Okay, this is also what remainder theorem tells us. So based on what remainder theorem tells us, what does this mean? This means when we plug in f of -1, we get 0, which is the same thing as the point -1, 0. Okay, so since it divides into it perfectly, there's no remainder left. That means that's a factor. All right, using factor theorem again, it says use synthetic division to divide, determine if x minus 2 is a factor of f of x. So I'll have you guys go ahead, pause the video and try this on your own, and then we'll see what you get. All right, so I made sure this is in order. I'm not missing any terms. Carry this down, start multiplying. And voila, I get a remainder of 0. So yes, x minus 2 is a factor of the function. Okay, now what this also helps us determine is, now that we know that this is a factor, I could rewrite this function down below as x minus 2, because I knew that divided into it, times what I'm left with. So this is, if we start with a third degree polynomial, this is an x squared, second degree polynomial, x, and then that's just a constant. So times x squared plus 4x plus 3. Okay, so I could rewrite this because I know when I divided this whole thing by x minus 2, this was my answer. So if I reversed it, I take this, I multiply it times x minus 2, I get what I started with. So the cool thing about this is when you can divide and you get a remainder of 0, and you know that that's a factor, you can rewrite your answer as that factor times your new quotient here. And that's what I was talking about on this page a couple slides ago, where you write down your factor times your new quotient, and then if you have a remainder, you tack that onto it. Here we don't have a remainder, so we wouldn't need to tack that on, but in other cases you do, and you will need to tack that on. So if we go back, for instance here, to this example, if I were wanting to rewrite this, I divided by x plus 1, okay? And what did I get here? This is cubed, squared. I got negative x cubed plus 4x squared plus x minus 1. And then all of that minus 9 as your remainder. Okay? Out of x plus 1. So that is what this looks like when you tack on the remainder, if you rewrite it in that factored form. Okay, rational roots and zero theorem. So this is probably a new one for most of you guys as well. So if we're given this big polynomial and it has integer coefficients, then what we can do to find any of the possible rational roots or zeros, meaning x-intercepts, is we can take p divided by q, and that will give us any of our rational roots. Okay, what is p, what is q? P is any factor of the constant term, so the last term. So it's a factor of the constant term. And q is any factor of the leading coefficient, so the first coefficient right there. So I'll show you guys in just a second what the heck I'm actually talking about. But we're going to divide p by q to get our rational roots or zeros. Okay, so this says list all possible zeros, rational zeros, of this function. All right, so we look and we see what the p values are. So the constant here, which is what we call p, that is -3. So that's the very last, that's a constant. And then the leading coefficient, what we call q, is 4. So these are p's, these are q's. All right, so what are the factors of -3? So what numbers multiply into -3? Well, plus or minus 1 and plus or minus 3. So +1, +3, -1, -3. Those all divide into -3. Then what are the factors of 4? +1 and -1, +1 and -2, and +1 and -4. So then, to find all of the potential x-intercepts or rational roots or zeros, again, that are rational, that can be written as a fraction, we divide the p's by the q's. Okay, so all the factors of the constant term divided by all the factors of the leading coefficient. So we literally just write these factors divided by these factors, and then we do every combination. So plus or minus 1 divided by plus or minus 1, so 1 divided by 1 is just 1. 1 divided by 2 is 1/2, so plus or minus 1/2. And then 1 divided by 4 is 1/4, so plus or minus 1/4. Then we look at the 3, so 3 divided by 1 is 3, so plus or minus 3. 3 divided by 2, so plus or minus 3/2. And then 3 divided by 4, so plus or minus 3/4. Okay, so these are all of our possible rational roots. The reason that we even have this theorem, or the reason that this is super helpful to us, is because, as you saw previously, when we can find out what one of the zeros is, or what one of the factors is, it makes our life really easy, because then we can divide into that polynomial and we can continue factoring eventually and find all the zeros. But if we don't know what one of those zeros is, then we have to find a way to find them, and that's what this method is for, or that's what this theorem is for. All right, so this says find all the possible zeros of this polynomial here. So I'm going to circle and label the P's and the Q's. All right, so P's are the factors of -8. So what numbers multiply into 8? So 1, 2, 4, and 8. Obviously, we're talking about just the whole numbers here. Okay, and then what numbers factor into or multiply into 2? Just 1 and 2. So all of our possible rational roots would be 1 divided by 1 is just 1. 1 divided by 2 is 1/2, so plus or minus 1/2. Okay, then 2 divided by 1 is 2. 2 divided by 2 is 1, so since I already have that accounted for here, I don't need to double write that. And then 4 divided by 1, plus or minus 4. Plus or minus 4 divided by 2, so 4 divided by 2 is 2. We already have that accounted for, so again, I don't need to write that. Okay, then 8 divided by 1, and then 8 divided by 2, which is 4, and again, we already have that. So these are all of the possible zeros or rational roots of this function, okay? All right, now we're gonna put this all together. We're going to utilize every single theorem. We're gonna talk about why do we actually care about these rational zeros and put it all together into one thing, and we've got just these two last examples, example 3 and example 4. So this says find all zeros, all of them, of this polynomial function, okay? So I want you to write down these steps right here first for me. Step number 1 to do this is we use rational roots theorem to list all of the possible rational zeros. If we're not given any of them, we have to figure out what are some of the possibilities at least. So we write those. Step number 2, we're going to use synthetic division to find one of those rational zeros. We know that any time it divides into it perfectly and we get a remainder of 0, that is a root, okay? Then after that, we'll factor and we'll set all the factors equal to 0 and we will solve. So I've written this on a separate page just so that we have enough space to write everything down. Okay, so like I said, step number 1, we need to list all of the possible rational roots. Or possible rational zeros. Again, those two things are interchangeable, those two words. Okay, so we need to find our P's divided by Q's. All right, here are the P's, here are the Q's. Okay, so P's divided by Q. So factors of -16 divided by factors of +1. So when you don't see a coefficient there, please write it in. That way you're not confusing it and writing x's. These should always just be numbers. Okay, so factors of 16 are 1, 2, 4, and 6, 8, and 16. And all of those have positives or negatives, plus or minus 1, 2, 4, 8, and 16, okay? Factors of 1, just plus or minus 1. Whole number factors again. All right, so all the possible rational zeros that we have here, if we just divide all of these by 1, we just get themselves. So 1, 2, 4, 8, and 16, and then negative 1, negative 2, negative 4, negative 8, negative 16, okay? So that's step number 1. We list out all of our possible rational zeros. Step number 2 is we have to actually find one of those, so we use synthetic division to find one of the rational zeros. Again, going back to our theorems before, let me go back a couple pages, right here. So factor theorem tells us if the remainder is 0, then C is a 0 and x minus C is a factor. So that's what we are looking for. All right. So I always just start kind of in order, and I usually start with dividing positive 1 and then negative 1 and then positive 2 and then negative 2. So we're going to use synthetic division, so I'm going to use 1 first, and I will write out all the coefficients here. So 1, negative 5. Okay, now we're missing a term here, so we've got to rewrite this. So 1x to the 4th power minus 5x cubed. I'm missing the x squared term in between here. So plus 0x squared plus 20x minus 16. Please, please, please make sure you are checking for that, because otherwise it's going to throw the entire thing off. So 0, 20, negative 16. All right, carry this down, start multiplying. So I get 1, add, I get negative 4, multiply times 1, I get negative 4. Add down, 0 plus negative 4 is negative 4. 1 times negative 4 is negative 4. Add down, 20 plus negative 4 is 16. Multiply 1 times 16 is 16. And then negative 16 plus 16 is 0. And oh my goodness, that is amazing news. It is our lucky day, and this does not happen often, that the very first rational zero you try to use actually ends up being a rational zero. That's the reason we say these are possible rational zeros. They are not all going to be zeros by any means. They're just the possibilities. Okay, so we know that x equals 1 is a 0 by factor theorem. All right, so we found one of those. Now step 3, we are going to factor and set all the factors equal to 0. So we rewrite what we have. We rewrite the function. So we have f of x equals our factor. So since x equals 1, that's our C term right here, then the factor would be x minus 1, opposite sign. Okay, that's the factor that we technically divided by. And then we write what we are left with. I'm going to write it in this color. So we started with x to the 4th power, so this is going to be x cubed, x squared, x, and then the constant. So we're left with x cubed minus 4x squared minus 4x plus 16. So when we divided by x minus 1, this is what we got. And then from here, we need to continue factoring this. So this part's already factored, but we need to continue factoring what's left in this parentheses. And then, since we're trying to find all the zeros, we set the whole thing equal to 0, and we solve for x. Okay, so to factor this guy right here, I look to see, can I use grouping method? Since this is an x cubed. So I actually can use grouping method, which is awesome. Okay, and I'm going to do that just separate, kind of over to the side here, before rewriting this out in front. All right, so x cubed minus 4x squared minus 4x plus 16. I'm going to group the first two terms and the second two terms, make sure there's a plus sign there. Then we look to see what the GCF is between each parentheses. So here I can factor out an x squared from both terms. And then between a negative 4x and a 16, I can factor out a 4. But I'm going to make it negative because I notice this first sign is negative and versus this is a positive. So if I want that to flip and match, I'm going to switch that, okay? So I get x squared times, this would give me x minus 4, then put the minus 4 out in front, and this would give me x minus 4 again. Okay, the x minus 4 is matched, which is exactly what we needed. So that's our new GCF times x squared minus 4. Now, again, you need to be really careful here and check to see if both of your parentheses are completely factored. So x minus 4 is, but the x squared minus 4 is not. Now I'm going to just rewrite this all down here since I factored that out. Okay, so I still have the x minus 1 out in front. The x squared minus 4, I can factor that a little bit further. So that's going to give me x plus 2 times x minus 2. Again, when this is a difference of two perfect squared numbers, remember you take the square root of the first term, so that gives you x, and then you take the square root of the second term, square root of 4 is 2, and then one of them has a plus sign and one of them has a minus sign. Okay, so now it is completely factored, which is awesome, and that's sometimes what takes the longest amount of time. So step number 4 in our process, if we look back here, says to solve. So we set the factors equal to 0 now, and we solve because we're trying to solve for the zeros. So when is f of x going to equal 0? So 0 equals this whole thing, x minus 1 times x minus 4 times x plus 2 times x minus 2. We use zero product property. We split up all the factors, set them equal to 0, and then we solve. And for this step, you guys, I am fine if you want to skip this and just jump directly to the answer of x equals 1, 4, negative 2, and positive 2. It's pretty easy normally for you guys at this point in the class to see what those are going to be. Okay, so we just answered the question, what are all of the zeros, or find all of the zeros. So these are all of our zeros, and if we write them as points, we'd have the point 1, 0, 4, 0, negative 2, 0, and 2, 0. So those are the 4 zeros that this polynomial has. So pretty cool. Without using a graphing calculator, you guys just checked or found what these zeros are. And what I would highly suggest is when you are doing these types of problems on your own, use a graphing calculator, use Desmos, plug this in, and double check that it actually does cross the x-axis at these points. That's just a really good way to go back and check your work. Okay, one more practice problem, putting this all together. This one will hopefully go a little bit faster. So it says find, again, all of the zeros for this new polynomial. First thing first, we've got to find all of the possible rational zeros. Okay, so we're going to find our P's and our Q's. P's and Q's. Okay, so P's divided by Q's give me, let's see, factors of 15 are 1, 3, 5, and 15. Factors of 1 are just 1. Plus or minus 1, okay? So all of our possible rational zeros are just plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. So let's go ahead and plug those in and actually find one of the zeros. So I'm going to start with, again, positive 1. I make sure this is all in descending order and we're not missing any terms. So x cubed, x squared, x, and then constant. So we're good. Okay, so 1, negative 7, 7, 15. Carry down the 1, multiply times 1, add to get negative 6. 1 times negative 6 is negative 6. Add 7 plus negative 6 is 1. 1 times 1 is 1. And then this gives us 16. So we know that positive 1 is not a rational zero. Okay, so I'm going to move on to the next one, negative 1. We've already ruled out one of those. So negative 1, oopsies, 1, negative 7, 7, 15. And sometimes you guys are going to have to try this process multiple times. You might have to try 3, 4, 5 times until you actually find a real zero. So negative 1 times 1 is negative 1. We add, we get negative 8. Times the negative 1 is positive 8. Add, we get 15. Negative 1 times 15 is negative 15. Add, we get 0. Yay, so we've got a winner here, okay? So we know that x equals negative 1 is a 0. And that means that x plus 1, so opposite sign, if this is our c value, is a factor. That's what factor theorem tells us, okay? So then step number 3, we go ahead and we rewrite our polynomial. So here I ended up with an x squared term since I started with an x cubed, and it's 1 less than that, and then an x term. So I've got x plus 1 times this whole thing. So x squared minus 8x plus 15. The nice thing here is that I see immediately this is a quadratic, and so factoring that is going to be pretty easy in comparison to some of the other polynomials you might be left with. Okay, so I'm going to finish factoring this. This one I can factor by guess and check because I have a leading coefficient of 1 right here. So I know that these are both going to be x's. Then I'm looking for 2 terms that multiply to give us 15 and add to give us negative 8. Okay, so that would be negative 5 and negative 3. So x minus 5, x minus 3. Step number 4, we have to set the whole thing equal to 0. Now that it's fully factored, and we set then each individual factor equal to 0 using zero product property, and we have our answer. So x plus 1 equals 0, x minus 5 equals 0, and x minus 3 equals 0. If you were to subtract 1 here, you get negative 1. Add 5 here, you get 5. Add 3 here, you get 3. Okay, so our zeros then are negative 1, 0, 5, 0, and 3, 0. Okay, pretty cool. So again, we're putting together a lot of different things here. Rational roots theorem. This gives us factor theorem. Also, this gives us remainder theorem because when we plug in negative 1 for function f, we get 0 out. Okay, and then we're using factoring, zero product property, and all of that stuff. So this lesson is a really big one, really, really important one, especially to practice the homework here because of how many different pieces and components you're putting together. So please go ahead, start on the homework, and ask if you have any questions.